Hi everyone. In this tutorial, we're going to be reviewing the ways that we can calculate an empirical formula or a molecular formula from a compound. As it turns out, there are a number of ways that we can actually begin a problem like this depending on what data we're given. Usually the most common format for these types of problems is to be given percent composition data for the compound. So, for example, we're told originally that this compound in this example problem has 72.2% magnesium and 27.8% nitrogen by mass, and they're asking for the empirical formula of the compound. Well, the first step in each of these problems where we're starting from percent composition data is to assume a 100-gram sample. All right, and the reason that's useful is that 72.2% of 100 would be 72.2. So there are 72.2 grams of magnesium present in the compound if we have a 100-gram sample. Similarly, if we apply that same logic to the amount of nitrogen, then that means that we have 27.8 grams of nitrogen. So that's allowed us to very simply convert the percentage data to mass data. Now, in order to find an empirical formula, that is a ratio between the amount of moles of each element present in the compound, not a ratio between the amount of grams. And so the next step is we're going to have to convert each of these grams of these elements to the corresponding number of moles. And so I'm going to need to convert grams of magnesium to moles of magnesium. So I'm going to need the molar mass, grams per mole. If I look in the periodic table, I should be able to find that the molar mass of magnesium is 24.31 grams per mole. And so if I go ahead, cancel my units, and do the math, that tells me that I have 2.97 moles of magnesium present in this compound. Now, if I repeat the process for the nitrogen, then I'm going to convert the grams of nitrogen to moles of nitrogen. And so grams per mole, the molar mass of nitrogen, if I look in the periodic table, should be 14.01 grams of nitrogen per mole. So if I cancel my units and do the math, then once again, I get 1.98 moles of nitrogen present in the compound. Now, in order to determine the ratio between the elements, then what I need to do is I need to divide by the smallest number of moles that I calculate from all of the elements in the compound. And so for this particular problem, 1.98 moles of nitrogen is less than 2.97 moles of magnesium. So I'm going to divide through in both responses by 1.98. So 1.98 divided by 1.98 is 1. Now 2.97 divided by 1.98, that's actually 1.5. Now, a common mistake that I see students make is that they'll say, okay, I'm going to go and I'm going to round 1.5 to 2, which means that my empirical formula is Mg2n. All right, that's incorrect. All right, basically, you can't simply round in this case. What you're going to need to do is think back to your decimal equivalents. So if I consider a number that ends in 0.5, 0.5 is the decimal equivalent of 1/2. So basically, this is the same as 1 and 1/2. If I want to create a whole number from 1.5, then what I'm going to need to do is I'm going to need to go and multiply by that denominator of 2. If I multiply 1.5 times 2, I get 3. Now, whatever I do to one element in the formula, I also have to do to the other. So I have to also multiply the answer I got for the nitrogen, the 1, I have to multiply that by 2 as well. So what that means is that there is a 3:2 ratio of magnesium to nitrogen in the compound, which makes my empirical formula Mg3N2. Now, as it turns out, since this compound turns out to be ionic, if we think back to our common ions, magnesium usually has a 2+ charge, and nitrogen forms the nitride ion, which would then have a 3- charge. If we cross the charges, then we would get Mg3 and 2. So that checks out based on the empirical formula that we figured out. Now, this particular step, where we had to multiply by 2, is actually something that will pop up from time to time in these empirical formula problems, depending on how the math shakes out. So if, as it turns out, you're doing an empirical formula problem and you get to this step right here, where you're trying to determine the ratio of moles between the compounds, if you have an answer that ends in 0.5, 0.5 is the equivalent of 1/2, so you would have to multiply that by 2 to get a whole number. All right. Similarly, if I end up with some answer that ends up with 0.33 repeating or very close to that decimal, or 0.66 repeating, well, those are the decimal equivalents of 1/3 and 2/3 respectively. And so that would mean that I would have to multiply those answers by 3 to get a whole number. If I get a decimal ending in about 0.25, then we recognize that as a decimal equivalent of 1/4, and I'd have to multiply everything by 4 to get whole numbers. All right, so keep an eye out for this. It doesn't happen super frequently, but it can happen in empirical formula problems. Now, I also wanted to talk to you quickly about combustion analysis. All right, sometimes if we are being asked to calculate an empirical or molecular formula, sometimes instead of being given percent composition data, like in this problem, instead what we're going to do is we're going to actually take a sample of compound, we're going to know its mass up front, and then we're going to burn it in oxygen, all right? And then from that data, all right, we're expected to then turn around and find the empirical formula in this case. And this problem also asks for the molecular formula. Well, the way that you handle these problems is by thinking about what a combustion reaction really is. We're told that naphthalene, this compound that we're given in the sample problem, only contains carbon and hydrogen. I use X and Y for the subscripts because we just don't know them yet. In any combustion reaction, we're going to go and we're going to react this compound with oxygen, adding heat to it. That's going to cause the compound to burn and produce carbon dioxide and water. Okay, but note that all of the carbon that was in the naphthalene got converted to carbon dioxide. And all of the hydrogen that was in the naphthalene, well, that got converted to the hydrogen that is now present in the water as a product. And so we can use that to our advantage. So we're told in this problem that when this combustion takes place, that we form 0.0103 grams of carbon dioxide. So let's start there, okay? We formed 0.0103 grams of carbon dioxide. I'm going to convert that to moles. So the molar mass of carbon dioxide is 44.01. I'll leave it to you to verify that yourselves. You guys can all calculate molar masses just fine. Now, as it turns out, so now I'm in moles of carbon dioxide. If I examine the formula of carbon dioxide, for every 1 mole of carbon dioxide, I have 1 mole of carbon atoms. All that really means is, if I look at the formula of carbon dioxide, for every one of those formula, there is a subscript of 1 understood associated with the carbon. So 1 atom of carbon for 1 molecule of carbon dioxide. We can extend that relationship to the mole scale and say that for every 1 mole of carbon dioxide, there's also 1 mole of carbon atoms. Now, I'm going to also convert the moles of carbon to grams of carbon. And I know that there are 12.01 grams of carbon in 1 mole of carbon. So if I do this math, then basically what's going to happen is I'm going to figure out how many grams of carbon there are present in the product. But by the law of conservation of mass, that means there were also that many number of grams of carbon in the naphthalene to begin with. So if I do the math, that comes out to 2.811 times 10 to the negative 3 grams of carbon. So as I said, basically that answer represents the grams of carbon in the carbon dioxide, but also the grams of carbon that I started with in my naphthalene. And if I started with 0.00300 grams of the naphthalene and subtract out the 2.811 times 10 to the negative third grams of carbon, then that should leave me with the starting mass of hydrogen that I had present to begin with. If I do that subtraction, that's 1.890, roughly, times 10 to the negative fourth grams of hydrogen. Well, now we have the grams of each of the constituent elements in the compound. I'm going to convert those to moles. So 2.811 times 10 to the negative third grams of carbon. Let's convert that back to moles. So divided by 12.01 grams of carbon per 1 mole of carbon. All right, that comes out to 2.341 times 10 to the negative fourth moles of carbon. All right, I'm going to convert the 1.890 times 10 to the negative fourth grams of hydrogen. Divide that out by 1.008 grams of hydrogen for every 1 mole of hydrogen. That comes out to 1.875 times 10 to the negative fourth moles of hydrogen. So if I go and divide by the smallest answer that I got, so basically in this particular case, the smaller of the two answers would be the 1.875 times 10 to the negative fourth, I can divide that out. And I'm going to get 1.25 to 1 as the ratio. Now remember what I said in the previous example. Basically, if an answer ends in 0.25, then I have to multiply both amounts by 4 to get the whole number ratio. So I'm going to multiply this by 4, I'm going to multiply that by 4, so that's 5 to 4. So that means that my empirical formula is going to be C5H4. Now, if you recall, we were also told that the formula weight for naphthalene is 128 AMU, so they want us to find the molecular formula. So let's review how to find a molecular formula. All right, I'm going to go and I'm going to find the formula mass for C5H4. Okay, now again, 5 times 12.01 grams per mole of carbon, or I should say AMU of carbon, times 4 times 1.008 AMU for hydrogen. That's going to come out to 64.082 AMU. I'll leave that to for you guys to verify. Now, what I'm going to do is I'm going to take the formula weight for the compound, which is 128 atomic mass units, and I'm going to divide that out by 64.082 AMU. That's going to come out to roughly 2. So what that means is, to get the molecular formula, I'm going to multiply each of these subscripts by this factor of 2. So that makes my molecular formula for naphthalene C10H8. Okay? So hopefully this review of how to find empirical formulas from percent composition data was useful. We will continue to discuss and practice these combustion analysis problems. They do come up every once in a while on the AP chemistry exam. Again, they can be somewhat long, right? But basically, as long as you take a methodical approach, you should be fine. If you have any questions, by all means, reach out to me, email. Otherwise, see me in class tomorrow, and I'll see you guys tomorrow.